Ladies and gentlemen, welcome to another session of the Nambani Academy. And today we'll be looking into physical sciences, grade 12, work, energy, and power. So the approach will be explaining the key concepts. Immediately after explaining the key concepts, we go directly into an exam type of question. Remember now with grade 12, we do not have more time in order for us to actually do basic things. We need now to integrate the lessons together with how the examiners are asking questions. But before that, we need to ensure that we solidify the foundation with the basic concepts that we can be able to fully understand. Because the thinking and the feel with physical sciences is always that let's have a solid foundation. Let's understand how the principles work. And once we understand the principles, it will be easy now for us to apply. Thank you very much, Tapelo, for being here. Thank you very much, Mr. Sekwi, for being here. The question that you asked Mr. Sekwi of which textbook am I using, I do not necessarily have a specific textbook that I am using. I am just compiling one set of notes, taking something there, taking something there that I feel I can be able to modify, and it will add value now to the lessons. So I do not have any specific textbook that I can recommend for you. Whatever you have will work for you, but remember the key critical thing is the terms and definitions that we are giving out in the Free State Department of Education. The other one will be the exam guideline, which will indicate to you the examinable content. What is it that is going to be assessed moving forward? So I do not have a textbook, but what I do is I use terms and definitions. So this booklet you will definitely get. It is also available on my website, which is www.nambani academy. You can easily get this booklet that we are going to try and use in order to explain the concepts of work, energy, and power. So I want now to give you a platform such that one can greet me back. Then I will be able to be in a position that we are together. Then I will start explaining the concepts. Tapelo, are you there?
I'm there.
Okay, thank you very much. Mr. Seku, are you
I'm
still
here,
with?
sir.
Okay, thank you very much, Tapelo. Mr. Seku, are you with us?
Yes, sir.
Thank you very much. So if you are with us, ladies and gentlemen, let's get straight into it and without wasting any time. The first key word that one needs to understand here is what is called work. And remember, all these words that are here are possible definitions that examiners are going to ask. It will probably, in most cases, be a maximum of 2 marks, everything that is here. But now we do not know what is it that the examiner is going to ask. What we need to do is very easy. We need now to follow these principles as they are. So these principles are going to assist me. These principles are going to assist us in order to understand some of the basic concepts. So I'm fixing my pen here such that it can give me proper writing pattern. So let's go into it. Like I'm saying, this will give us now a maximum of 2 marks. The very first one is now the word work. And work is defined now as work done on an object by a constant force is the product of the magnitude of the force, the magnitude of the displacement, and the angle between the displacement. Let me quickly explain that. Me explaining that, I will need to have a diagram. Let's say we have a surface here, which is in this instance will be a frictionless surface. I am going to have a diagram, and this diagram I'm just going to fill it with blue for the purpose of explanation. And now I am going to apply a force, and this force, it is now in that particular direction. So this will be my force applied. Remember I said we are working now with a frictionless surface. We know what is a frictionless surface, grade 10, grade 11, and now in grade 12 when we worked with Newtons as well as in grade 11 as well. So the key thinking here is we need to have an angle at which now the force is acting on. And that angle, we know that our object will move in the direction of the net force. I'm not sure what is wrong with this pen. It's acting up somehow. Let me just quickly fix it. It should be better now. So now we know that this object will move in this particular direction, and this direction is what we call the displacement. So the angle between the displacement is what will necessarily tell us that are we going to have a positive work or are we going to have a negative work. I will explain that. We say if F applied, or if force is in the same direction with displacement, use theta to be equals to 0. Something is very wrong here. This pen shouldn't be doing this. This pen should not, seems like it's not calibrated well. Better. Let's write it nice and clean. Fine, better. Let's see. Now, if force is in the same direction with displacement, use theta is equals to 0 degrees. So we check the direction of the force and the direction of the displacement. So if the direction of the displacement is in the same direction as the force that is being applied, we use 0. So if I were now to change the direction of the force, but the object is moving in an opposite direction, I am forced now to use an angle that is now 180 degrees. So let's write it now in red to put emphasis on it. So if force is in the opposite direction with displacement, theta is equals to 180 degrees. That is now very, very important. Now, I am going also to be explaining that from the equation, which is W is equals to F multiplied by delta X cos of theta. I know some textbooks and some people out there will preferably say, yes, the angle you can use now depending on the information that is given. But I want us to be cautious of one thing, and I am going to try and assist you. I want us to be cautious about one thing. This theta, I want us for all the examples and problems that we are going to do, to keep it now to be between, to be only 0 and 180. That will assist us in terms of now not confusing everything in terms of the angles that will be given. So as doing that, we know once we work with work equation that is now in symbols, we know that theta will only be 0 and 180. Then one will ask, why 0 and 108? The emphasis was put when we said if the force is acting in the same direction as the displacement, we use 0. So we must just check the direction of the displacement. If the force is acting in an opposite direction to the displacement, then we use theta is equals to 108. Now, there will be questions in an exam that asks, is the normal force doing work on an object? The angle thereof, when we draw, we are going to have, let's take yellow, we are going to have our normal force in this direction, which is always upwards. It is exerted by the surface on the object. So it will be making an angle of 90 degrees with the displacement. So once it makes an angle of 90 degrees with the displacement, it basically says now no work is done. The SI unit for work, it is now in joules. So this is one important concept that one must now start to understand, that when we work with the work equation, is basically representing each and every individual force that we have from our correct free body diagram. So I am going to pause, give you your 30 seconds such that you can digest now this issue of 180 and 0. Also ask now your questions if there's any relating to the basic concept of work. This is now in terms of the definition itself, in terms of how best can we apply the work equation. So once we are able to do that, believe you me, it will be easy for us to build on this particular other concepts. So your 30 seconds starts now. Thank you very much, Mr. Sekwi. Your hand is up. Kindly ask your question or any comment that you want to raise.
So is it always going to be 0 and 180 or can it change?
Is it always going to be?
0 and 180, 180.
Thank you very
Or
much,
can it
Mr.
change?
Sekwi. Uh, I want to put my head on the block and say it will always be 180 and 0. You'll see when you do examples, there are many ways of killing a cat, as people will always say. But my intention is once we get to a stage where we have an inclined plane, because now check the diagram that I drew. The object is just sitting horizontally on the surface. Once now we have an angle, a force applied at an angle, the object being on an inclined plane, everything now changes. That is where the problem comes. You find now learners substituting the value of angle of inclination into this particular equation. So I have seen, and the history has taught me that it becomes a problem. And once it becomes a problem, people do not now understand exactly the approach of 180 degrees and 0. So once we are confident that we are able to understand when is it 0 and when is it 108, then we can introduce other methods of now killing the cat. But for now, we keep it now nice and clean in terms of what? In terms of 0 and 180 degrees. Is it clear, Ntatesekwi?
Yes, sir.
Is it clear, Tapelo?
Yes, sir.
Thank you very much. So now let's move to the next concept. And the next concept is positive work and negative work. I'm going to take red and write here to say once we use 180 degrees, cos of 180 degrees is equals to minus 1. Cos of 180 is equals to minus 1. I'm going to write it there and say cos of 0 is just equals to 1. So let me highlight so that we know where we are in our pages. Now, the issue of positive work and negative work comes from the angle that is now parallel to the surface. Hence, we are only going to use 180 and 0. But what does it mean when we have a positive work? It basically says the kinetic energy of the object is increasing. That is very, very important. So positive work basically means the kinetic energy of an object is increasing. Hence, we are going to have now that positive work that is being done there. So positive work, kinetic energy of the object increases. Negative work, the kinetic energy of the object decreases. And this makes sense because once we introduce friction, let's draw a force which is a frictional force. Once we have friction acting there, obviously, just going to make it somehow something like that. Once we have friction, the reason why friction is there is basically to reduce motion. So if motion is reduced, it basically says the kinetic energy of the object is decreasing. That is very, very important. So the case of positive work and negative work is influenced by the angle that is now applied parallel to the surface, either 0 or even 180 degrees. When this 2 is explained, let's move now to work energy theorem. Let me clean this board. I want us now to go to work energy theorem. Work energy theorem. And again, let's have our diagram. And we introduce a force applied in this direction. And let's have the surface. But in this instance, I want us to introduce friction. So I must say this one, we have friction. It says now, the total work done on an object is equal to the change in the object's kinetic energy. The total work done on an object is equals to the change in kinetic energy of an object. What does this say to me? It says for me to use work energy theorem, I must be now in a position of calculating the F net. I must actually know what is the value for F net. Once I can calculate the value of F net, it means I can be able now to apply this principle that is now called work energy theorem. So with work energy theorem, it is one of the energy principles. So let's have friction here. And the first question that I'm going to ask will be, let's draw a free body diagram. Let's draw a free body diagram. And this free body diagram, it's 4 marks. I want to show you why. We have the force applied in this direction. We are also going to have our Fk. We are also going to have our normal force. We are also going to have our Fg or Fw in this instance. Ladies and gentlemen, we said once we have cos of 90 is equals to 0. So everything multiplied by 0 is 0. Which brings me now to this particular diagram also that we have drawn. It basically says work done by Fn is equals to 0 joules. One can also say work done by Fw is also equals to 0 joules. Then one will ask, but why? Because the normal force is acting perpendicular to the surface. Fg or Fw is also acting now perpendicular to the surface. So because of that, we know that now the angle between the surface or the displacement and the force is going to be 90, and cos of 90 gives us now this 0. So everything that is now acting perpendicular to the displacement or to the surface or of the object, it will definitely give us no work. Hence, we are going to have work done by, work that is 0 joules for Fn and 0 joules for Fw. But now I still have these two important forces. I still have these two important forces, Fa as well as Fw. If I were to be given the magnitudes, this will be 20 newtons, this will be now 5 newtons, let's write it here, and this will be 20 newtons. Can I calculate F net? Definitely I can. So F net is just now the sum of Fa plus the sum of Fk. This becomes now 20 minus 5, which will give us 15 newtons. But what is it that work energy theorem is saying? It is saying to us the net work done. So work net is equals to the change in kinetic energy of the object. How can one get work net? We can easily say now work net is equals to F net multiplied by changing x cos of theta. But what does this say to me? It says I need now to know the magnitude of F net. So work net is actually all the work done by each individual forces that are acting on the object. So what is the kinetic energy? We know from grade 10 that kinetic energy will just be now half of mv squared final minus half mv squared initial. So this becomes what we call work energy theorem. Ladies and gentlemen, I am going to put my head on the block and say this one always always works. Always works. But it only works when we are told that use energy principle. So work energy theorem is one of the principles that we associate with energy principles. So work energy theorem, you must just know that you need to state it and also be able to apply. The instruction will be clear at times. Use work energy theorem. So what are we expecting? W net is equals to changing EK. This must be now your first point of reference when working with work energy and power. So work energy theorem, its work net is equals to changing EK. And this will be given now in your table of a formula sheet or formulas. Then you can just remember to use now the weight net for total or total work done on an object is equals to the change in object's kinetic energy. Then you will be able to get your maximum of 2 marks. The application will come and it will be clear why do I need now to draw a free body diagram. So the free body diagram informs me in terms of which forces are actually doing work. Hence, I was able to say, but when I look at Fn, it is just going to give me 0 joules. When I look at Fw, it is just going to give me 0 joules because the angle is going to be 90 degrees. Therefore, I am interested in the forces that are actually doing work on the object. So when working with work energy theorem, please draw a free body diagram. Whether the examiner is asking for a free body diagram or not, kindly draw a free body diagram. A free body diagram indicates W net is equal to net, and substitute the F net into the equation, multiply by the displacement, and F net obviously will be somehow parallel to the surface. Is then that we only choose, Mr. Sekwi, 0 or 108, depending on what? The direction of the net force. So I am going to give you your 30 seconds for you to digest everything that has to do with work energy theorem, and then we can move now to another important concept. Kindly feel free to ask your questions such that I can be able to assist you. Let me go into it directly and say I don't see any hands from the chat. I don't see any messages. Then it basically says we are clear in terms of the application of work energy theory. The exam type questions, obviously, it is a combination of different concepts. And once it is a combination of different concepts, it is better off for us, because remember, our sessions are not your normal school sessions. So we are relying on finishing the concepts quicker and be able to explain other important things. So let me clean this board of mine and go now to principle of conservation of mechanical energy. This we have done it in grade 10, and once we did it in grade 10, it links from grade 10 to grade 12. So examiners can ask anything. So I am going to say, let's write important things about principle of conservation of mechanical energy. It says the total mechanical energy of an isolated system remains constant. The total mechanical energy. So it basically says to me, I am going to have EP plus EK at a certain specific position. So I am going to say initial is equals to EP plus EK final. It's easy to see. Or from grade 10 also, we also know that this is just mgh plus now half mv squared initial. We also know now that this will be mgh plus now half mv squared final. So what is common throughout? It's I am looking at the mass. So it basically says it is a hint that the examiner will be in a position of saying, I am only working with one object here. So once we see one object, chances are conservation of mechanical energy. But what will be a confirming words for me to be able to apply conservation of mechanical energy? We said, ladies and gentlemen, work energy theorem always works. But when we said it always works, the emphasis was one must draw a. So what is key critical now, such that you can be able to differentiate when to apply work energy theorem and when to apply a principle of conservation of mechanical energy. This is very, very important because most of us, we make a mistake now of we can only apply this principle if there is no friction. So once we are told there is no friction, it says that system is isolated. So once the examiner tells me there is no friction, chances are 100% that principle of conservation of mechanical energy will definitely work. We must also look for alternative words such as frictionless, such as ignore friction, ignore air resistance. So once the examiner tells me that no friction, that is a hint for me that principle of conservation of mechanical energy is applicable. Remember, what did I say? I said it is in the form of an exam, whether the examiner asks work energy theorem or principle of conservation of mechanical energy. Even though work energy theorem always works, the direction that the examiner wants to ask will be use energy principles. So the teaching in here should be which energy principle is more applicable. Is it work energy theorem? Yes, that will be my first point of reference. Is it now conservation of mechanical energy? Yes, if I am told that there is no friction, I can be now in a position of also using it. It further says, a system is isolated when the resultant force or net external force acting on the system is zero. It is an important definition that has been assessed over and over again. Learners are not getting it right. So remember, you must also be able now to define what is an isolated system. So an isolated system is a system when the net force or the net external force acting on the system is equals to zero. But remember, I want us to use the equations for us to remember the definitions. So from that, it's easy now for me to say the total out to say I can only use principle of conservation of mechanical energy provided now the examiner is telling me that the system is frictionless. The system ignore effects of friction, ignore air resistance, anything that will be a hint that there is no friction. It basically says mechanical energy is conserved. So mechanical energy will only be conserved provided that we do not have frictional force. So that's basically it about principle of conservation of mechanical energy. I am also now going to give you your 30 seconds for you to digest everything here so that I do not bombard you with a lot of information. And this should not be a talk show, it is a lesson, it is a class, such that now you can be able to process every little thing that we are building towards. Thank you very much. I am receiving a lot of questions on the other platform. I will attend to that once I am done. So long, let's just try to save time and explain all the concepts, because the key idea is in 2 hours we explain all the concepts. Then the next session we do exam type so that you can easily refer to the recording of the video, and we have saved time. We have actually completed the syllabus very early. That is the key idea of how to approach this thing. Now, we are done with principle of conservation of mechanical energy. Maybe before that, I should just check. Tapelo, are you still okay in terms of work energy theorem, principle of conservation of mechanical energy?
I'm okay, sir.
Thank you very much. Realebo
I'm okay.
Hasekwi,
Yes, I'm okay, sir.
if you are fine, then thank you very much. Let's move, gentlemen. We have conservative force, sorry. Now, how best can one explain this? A conservative force. Let's look into it. A conservative force is a force which work done in moving an object between 2 points is independent of the path taken. Allow me to write conservative force here. I want to explain what this actually means. Let's consider a projectile that we did in term 1. We definitely know what is a projectile. So when the projectile is thrown up, when it is moving up, what is the direction of the weight? It's always downwards. When it is thrown down, what is the direction of the weight? It is always downwards. So regardless whether the object is moving up or it is moving down, the direction of G does not change. So this basically says it is independent of the path being taken. So FW, we consider it now as a conservative force. Because why? It is now a force for which the work done in moving an object between 2 points is independent of the path taken. It does not rely on the path. So whether the projectile is going up, FW is going down. Whether the projectile is going down, FW, it is still going down. So it basically says it is not relying on the path that the object is going to travel. So a conservative force is a force for which the work done is independent of the path taken. So we usually get confused to say, what does this independent path basically means? It says It is not relying on any form of the path taking. So whether hence a projectile, because it's what we did in term one, we were told and asked in an exam, what is the direction of FW or FG? It is always downwards. Whether the projectile was moving up, whether the projectile was moving down, definitely FW is always. So if this is the direction, like we said, if this is now the direction of the object, why is not FW changing? Because FW is now what we call a conservative force. So a conservative force is basically a force for which the work done is independent of the path taking. Ladies and gentlemen, it says here examples are gravitational force, which is what I now explained. Elastic force in a spring and electrostatic force or Coulomb forces. For work, energy, and power, we will forever be looking into the gravitational force. Because now, when regardless whether we have an object that is now horizontal, an object that is now in an inclined plane, definitely, ladies and gentlemen, FW or the gravitational force will definitely be there. So I have just completed another part, which is the concept of work, of the conservative force. So it's only fair to give you now the 30 seconds. Remember, the 30 seconds is for you to digest and try to follow and understand exactly what each concept basically mean. So let's have the 30 seconds for us to digest, drink a little bit of water so that you stay hydrated and refreshed. Then we will move now to non-conservative force. Thank you very much. I don't see any questions. Mr. Sekwi, are you still there?
Yes, sir.
Thank you. Tapelo Ezekiel, are you still fine? Thank you very much. Then let's move to non-conservative force. Non-conservative force. Non-conservative. Non-conservative force. Let me draw an object. Add a force applied in this direction. Let's have another object. Add force applied in this direction. Obviously, let's have a surface. Very important. Let's have a surface. Very important. And then we say we are given mu k, which is equals to 0, 0,2. We are given mu k, which is just 0, 0,2. Basically, the surface is the same. The only thing that is changing is the direction of the force applied. then the easiest thing will be, let's draw a free body diagram. I am going to have my Fn, my force applied, my frictional force in this direction, and have my Fw. Can you do it for this other object? Yes, I can have my Fw, I can have my Fk, and then I can have my F applied, and I am going to have my Fw. Sorry. Now, let's read what the statement is saying. A non-conservative force is a force for which work is done depends on the path that is taken. Yes, Resekwi.
There on the second free body diagram, sir.
Mm.
Why is there two FW, sir? May I ask?
It's Fn, my brother. The writing is very bad. It is Fn, and that is Sekwi. It is not a W. Sorry, my brother.
Yes, sir. I was confused, sir.
Okay, no problem. Thank you very much. Now we have that. Let's read the statement here. A force for which the work done depends on the path taken is true. Let's check. For diagram A, when I pull the box to the right, frictional force is acting in an opposite direction. For block B now, if I change the direction of the force applied, the frictional force is also changing the direction thereof. So frictional force, it's depending on the direction of now what? The object. If the object is moving to the right, frictional force is moving to the left. If the object is moving to the left, frictional force is moving to the right. Hence now, per definition, it says a force for which the work done depends on the path taken. So the examples of that are frictional force, air resistance, tension in a string, and so forth. But in our cases, it will forever be friction, air resistance, and tension. So frictional force, it's a non-conservative force. A non-conservative force is a force for which the work done depends on the path taken. So the path taken influences now the direction of the frictional force, influences the direction of the tension. So that being said, it makes it easy for one to know that, okay, if the examiner wants me to define a non-conservative force, or identify a non-conservative force, it should be a force that depends now on the path taken. If I can apply the force to the right, it will move to the left. If I can apply the force to the left, it will move to the right. But it basically is for one just to know that these are few of the examples that we have. So hence I said this particular terms and definitions are very, very important because they actually give us or provide us with a guideline of what needs to be done in an exam. So I have explained now what is a non-conservative force. But while I am there, it is advisable for me now to add this other element. It is important now for me to add this other important element. I want us to consider work, okay, non-conservative force or work done by non-conservative force as another energy principle. I will explain why. We have an equation which is W and C is equals to change EK plus change EP. This equation relates now to work done by a non-conservative force. Very, very, very important. So it means if the examiner now says use energy principles to calculate whatever, once there's tension, once there's frictional force, I can not use conservation of mechanical energy, because conservation of mechanical energy, we agreed to say the examiner must say frictionless. So if I have three uh, energy principles that I can choose from, it always says I will always have two options to use. Work energy theorem, that always works. If I am told there is no friction, principle of conservation of mechanical energy jumps in. If I am told the friction is there, principle of conservation of mechanical energy falls out. I am only now left with work done by non-conservative force. That is the system or the principles that we use to minimize the confusion in the exam. Work done by a non-conservative force. So don't complicate the science. Read what the examiner has given you. Follow through in terms of what is it that you have. What you have will always be important in terms of giving you hints or ideas on how to apply. So remember, work energy theorem always works. If there's friction, then you use work done by non-conservative force. If there's no friction, then you can use a principle of conservation of mechanical energy. I hope that is clear, and I have just explained another concept, which is now work done by non-conservative force. So with that being said, let's have our 30 seconds to digest and move on to power. Thank you very much. I don't see any questions from the guys that are in here. Let's go straight to power. Power is defined as the rate at which work is done or energy expended. Let's just say the rate at which work is done. The formula is there in symbols. P is equals to W, which is work, over time, and time must be in seconds. Let me emphasize that. Time must be in seconds, and this must be now in joules. Just J. And the SI unit of power is watt. It's as simple as that. But what does this say to me in that number? This says to me the difficult work, oh, sorry for the irony, the difficult part is to calculate work. Once I can calculate work, I can just come here, substitute the work, and substitute the time. Then all the concepts are done. Can we apply now these concepts, of which, remember, at school you will be now doing it for 2-3 weeks, but the approach that I have is explain the concepts, solidify the foundation, get the PDF notes that I am going to share with the people that now registered for the academy. That is an extended bonus they have. They can easily get these notes and all the annotations that were made here. So already it gives you now an upper hand in terms of what needs to be done. So I want us now to try and apply this to an exam question that was asked some time back and see if what we have learned from this point to defining power, have we actually understood the little basic things we have. Remember, I am going now to give you the summary. Sorry, this summary, ladies and gentlemen, it what has helped me also to have an understanding of work, energy, and power. When the examiner says use energy principles, what is it that the examiner is actually saying? When the examiner says use energy principles, what is it that this examiner is actually saying? The examiner is saying use either work energy theorem, conservation of mechanical energy, or work done by non-conservative force. Those are the three energy principles that we have. One will say that number you are creating a misconception for you to say work done by non-conservative force is an energy principle. I added it to be an energy principle because it relates to work and energy. The work done by frictional force, and also it relates to the kinetic energy of the object as well as the potential energy of the object. Hence, I added it here to become part of the energy principles. Now, I have indicated a short approach of what needs to be done. When you are going to use work energy theorem, please, let's use purple, please draw a free body diagram. Identify all forces that are doing work. And immediately thereof, the equation that you must start with, you can manipulate everything later and what. When the examiner says now use work energy theorem, this is the equation. This is the equation that one must use. And I did say this one always works. So if things get difficult, this will be my go-to energy principle. That will be my go-to. But now I still have other two options and I don't want confusion in the exam or in a test. Conservation of mechanical energy. I must know now the definition or stating it, the total mechanical energy in an isolated system is conserved. So what must the examiner do? The examiner can either tell me that the system is isolated. I am looking for keywords which will say no friction, no air resistance, frictionless. That is only when I can be able to apply the equation mgh plus half mv squared initial is equals to mgh plus half mv squared final. So these are hints of us being somehow in the right direction. We are busy with the basic concepts. Energy conservation of mechanical energy. Examiners can also combine concepts of momentum to conservation of mechanical energy. But that we will do later once we are happy that we are able to apply work energy theorem. We are happy that we can be able to apply conservation of mechanical energy. When can now I apply work done by non-conservative force? Once there is friction, this will work. Once I am told there is air resistance, that will definitely work. Once I am told that there is tension, that should also work. So the method of thinking is to basically do what? Very easy. Check the forces given. Check the information given. So the hint is two will always be applicable. So if there's friction, work energy theorem will work done by a non-conservative force will work. If there's no friction, then work energy theorem will work and conservation of mechanical energy will also work. So once the examiner says energy principles, be on the lookout for that. I usually say these questions are about 5 to 7 marks. So if things get complicated, you will still be able to get a 5 out of a 7 only because of you followed the correct principle. You will be awarded marks for the correct formula, correct substitution and everything like that, and only lose marks maybe in the manipulation of the mathematical skills. So ladies and gentlemen, with this being said, I have explained a summary of energy principles and everything that relates now to work, energy, and power. So I am going to expose you to one or two questions that we can try and do together in order for us to actually see if this system is assisting us. So while we prepare for that, get your calculators ready and I will give you now the last 30 seconds for us to digest and be ready now to write a few. So I'm going to give you a question. We attempt to do it. You send me your answers and immediately after getting the answers we discuss, because now I don't want me to be the one doing it. I want you to attempt to do it such that when we explain, when we discuss, you can easily pick up the mistakes that you did. So I'm going to, what's the word, give you a timer with a question and you attempt to do the question applying all these nice principles that we spoke about. It will be difficult at first, but definitely there's a minimum mark that I want us to actually get. That is now 60% of the question we should get it right. The 70% moving up will only be an issue now of where did the examiner try to trick us, because there's always such a thing, but other questions are just straightforward that one can easily follow. So I am going to give you, let me not give you the 30 seconds, let me actually give you the question, and it is 15 marks. So I'm going to try and give you also something like 15 marks, or sorry, 15 minutes. It's exactly 19:15. So at half past, we will discuss how you tried to do this such that now we can look into that. So I'm going to give you 15 minutes. It's only fair for you to finish this. I understand the time might seem longer. It is intentional because I'm not testing the speed. I'm actually testing that we are able to understand the questions. Once we are confident enough, it's easy. We can shorten now the time. So remember, you send your answers directly to me. You have my number. Then I can look into what we have done and we definitely discuss. So with that being said, let's start. Yes, Tapelo. Tapelo, your hand is up.
Yes, I just wanted to ask where do we send question answers?
To my personal number, the one that we spoke on.
Okay.
Thank you. send me something. Re a leboga. And then we can be able to explain everything here. So I'm just going to give you an extra 15 minutes. Sorry, not 15, 2 minutes for you to kindly send me what you have so that we can see your progress on your side. So immediately after these 2 minutes, then we will discuss. Thank you very much. Let's not waste time and look into it. I'm going to start now with 15.1. Let me maybe use black. It says now a 70 kg block initially at rest. So we know now V initial is equals to 0. At the bottom of a rough plane means there's friction at an inclined angle of 30 degrees to the horizontal. The box is pulled up the plane by means of a light inextensible rope held parallel to the plane as shown in the diagram below. The force applied now is 700 newtons. Now, look at 15.1. What is the name given to the force in the rope? So Tapelo, the examiner is asking about the force in the rope. Yes, we have the 700 that is applied, which is the applied force. But basically what the examiner wanted to understand or to assess is us knowing that once there's a rope and we apply a force, that force is actually called the tension force. Why? Because it has applied through the use now of a string or even a rope. So the examiner will not give us or tell us it's a force applied there and ask now that the force must be first applied again at 15.1. So let's remember, once it is in the rope, it becomes now the tension force. That will now be the 1 mark. That is now at 15.1. At 15.2, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. It's very easy. We said now for mechanical energy to be conserved, we don't have to have friction. So in this instance, the examiner told us that this is a rough horizontal plane. Rough horizontal plane. So we have friction. So the system is not isolated. So one can just start by saying there is friction. And once there is friction, it basically means the system is not isolated. Furthermore, one can say the system is not isolated because there's friction, but I don't want to give you a lot of different answers or other options. We just say now there is friction, which is just another 1 mark. The box is pulled over a distance of 4 meters. So we are told that we have a distance now somewhere here of 4 meters. The kinetic frictional force between the box and the plane is 178,2 newtons. Draw a free body diagram. Let's do that. That is now at 5.3. 5.3, let's draw a free body diagram. Let me have my dot and fill it with black, and can make it black also. Fine. Now what I usually do, such that I do not confuse my diagrams, I usually have a plane here, and this plane, it basically represents the surface. Now I can add my arrows. I know I have the tension force in this direction. I have my frictional force in this direction. And I am going to have my F normal, which is now acting perpendicular to the surface. This becomes F normal. And I am going to have my FG, which is always acting downwards. And that. And now I am going to add my labels. This is very, very important. Let's add the labels now. This would become the tension or the force applied in this instance. And then this becomes our Fn. This becomes our Fk. This becomes our Fw. Now, there's a catch here, ladies and gentlemen. This is what you will get maximum marks for in the exam. Once the examiner says it is 4 marks, we are expecting 4 vectors. Ne? But there is a catch. What is the catch? The catch is we are on an inclined plane. So I am going to draw another free body diagram and have Ft for tension, have frictional force, have Fg perpendicular, have F normal, and have now another one which is Fg parallel. So why this free body diagram with the components? This free body diagram with the components, it is the one that now indicates all the forces that are doing work. So all these forces here are the forces that are actually doing work. So what does that say to me? It says now, once I am on an inclined plane and the examiner Tapelo asks me for a free body diagram, I'm going to give him this free body diagram of 4 vectors. But for the purpose of calculations, let's emphasize that. For the purpose of calculations, it is entirely important to have now what? A free body diagram with the components such that you do not miss any force that is going to assist you in terms of your calculations. So this we are just going to use for the purpose of calculations. Let's be clear on that one. So the correct one is the one that is drawn in black. The one in red, we are just going to use it because we are now where on an inclined plane. If we're not on an inclined plane, we can just draw any one because we do not have components. So we draw the one with components on our question paper just to check and know which forces do we actually have. So that is it now with 5.3. 15.4. Calculate the work done on the box by the frictional force over 40 meters. The direction of motion, it's in that direction. That means up the slope. So at 15.4, let me use black. At 15.4, W done by Fk is equals to Fk multiplied by changing x cos now of theta. Now let's check what we have. We have 178,22 multiplied by 4. Now we are worried now which angle should be there. Is it going to be 0? Is it going to be 180? Let's check the direction of the motion. The motion is upward. It is in the same direction as the displacement. So if it is in the same direction as the displacement, we are going to use 180. Your hand was up, and that is Sekwi.
So I was going to answer that it's going to be 187.
It is going to be 180 because it is acting in an opposite direction. Then we come to that and say fine. Then our final answer must be something like negative 712,88 joules. So that becomes now an easy 3 marks. One for the formula, one for the whole substitution, one for the correct answer with the minus with the SI unit. Then we get the 3 marks. Now, ladies and gentlemen, look at 15.6. It says use energy principles to calculate the speed of the box after it has moved 4 meters. Use what? Energy principles. What is energy principles? Work energy theorem, conservation of mechanical energy, and work done by non-conservative force. What did we say? Easy. We said we know that work energy theorem always works. So I'm going to make work energy theorem my first attempt and see if it is going to assist me. Work net is equals to changing EK. But which forces are now making work net? Easy. It's work done by tension plus work done by friction plus work done by Fg parallel is equals to change in EK is equals to change in EK. So what must I do now? I must actually calculate the work done by each individual force. I must actually calculate the work done by each individual force. Let's start with work done by FT. FT is given as 700. What is the displacement? 4 cos of, is it in the same direction as the displacement? Yes, then it must be 0. Plus work done by friction. We calculated work done by friction. It's minus 712,88. What is it that is left? Is work done by FG parallel. Now, where does this take me now? It takes me back now to Newton's laws. What is FG parallel? FG parallel is just mg sine theta. Maybe I must write it here to say FG parallel is just mg sine theta. So allow me to calculate this. It's 79.8 sine of 30, and then it will give me an answer here. Let me quickly get my calculator. Let me quickly get my calculator because I want us now only in the equation of work we substitute only 0 and 180. Hence I said once you want now to put everything into one space, it gets complicated, it gets confusing, so it is always better to have a system to use. So let's see, it's 70 multiplied by 9.8 multiply by sine of 30, and this gives us something like 343 newtons. Then what can we do? 343 newtons multiply by 4 cos now of what? Is it in the same direction as the displacement or opposite direction? Opposite direction, so is equals to 180. Then what do we have? It's half of 70 multiply by, it was, that is what we are looking for, final v squared plus, now let me do a big bracket, minus half of 70 into 0 squared. That is what now we are looking for, application of that. Then you just do the mathematics and eventually you find that VF is just equals to 4,52 meters per second. And the examiner said speed, so speed is a scalar quantity, no direction it's needed. So what is important here? Very easy. We used work energy theorem. I am going to try and see just one step of using work done by non-conservative force. Work done by NC is equals to change in EK plus change in EP. Which forces are non-conservative forces here? There's a rope which is now bringing tension. This will be work done by tension. There is friction, which is a non-conservative force, work done by Fk, and now change Ek plus change Ep. Then everything else will fall into place and become very, 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 very clear. Very, very, very clear. That will be very easy for one to actually understand. So this becomes our option number two. So hence I said this one here becomes option one. Very, very easy. How did I know which principle to use? Work energy theorem always works. That is a secret hint that I'm giving you. Then, are we having a rough surface? Are we having a tension? Yes. Then work done by NC should also work. And the question did ask, is this an isolated system? No, it's not isolated because there's friction. So conservation of mechanical energy will definitely not work. So ladies and gentlemen, with that being said, it brings us now to saying, Tapelo, your hand is up.
Yes, in that option two, you don't include work done by FG pilot.
FG parallel, let me check. We must include FG parallel, but FG parallel, it's not most, what is the weight? It's not a non-conservative force. It is a conservative force, so it will not be part of the calculation.
Okay,
Yes, sir. So
that's it.
hence it was important for one to fully understand the difference between conservative and non-conservative. So FG parallel is a component of weight, so it is actually a conservative force. So it will not be part of the calculation.
Makes sense.
Thank you very much. Ndate Sekwi, are you still there? Are you happy?
Yes, sir, I'm good, sir. Thank
Thank
you.
you very much. Now, ladies and gentlemen, that 15.6, we will do it some other time. It's just 1 mark. That's not a problem at all. We will look into it. The key thing now is it's 1955. So I want you to give me a reflection of today's lesson in a quick 1 minute to 30 seconds to 1 minute. I will start with you, Tapelo, to say what is it that you are taking from today's lesson. Remember, I'm going to give you one extra question that you can do, and then we mark for tomorrow so that tomorrow we can know that we have something to mark, we have corrections to make, and then immediately build onto another type of problems. So let me start with you, Tapelo. What are your reflections for today's session? Tapelo, your reflections for today's session?
Uh, I thi- I've managed to see my mistakes. Like I forgot that FG parallel they work on this topic. I thought they only work at
Newton's laws.
in Newton's law. So
Okay,
that was all my problems.
okay.
I,
Thank you. Thank you very much. It's important now to incorporate, I usually say, let's incorporate Newton's laws with work, energy, and power, and everything will be easy. Because once, if the free body diagram is incorrect, automatically you are going to lose other marks somewhere. Hence, I said we mark the one in black. That is the one that you must give. But once it is on incline, you must have this extra one that shows now the components. That is when we miss a lot of marks because we do not consider uh, forces applied at an incline. So this question was solely chosen for such a mistake. So I was happy when I saw that there's such a mistake. It basically says, let's correct it. Moving forward, we will be clear and know what to.
Second law and all the questions right now, sir.
100% same. So what does it say? It says now when we work with work energy and power, reference should be Newton's second law or Newton's laws. So by so doing, it basically says in question 2, we'll be able to get maximum marks. In question 5, which will be working Asian power, we must also be able to get maximum marks. But now let's not forget this issue of energy principles. This section is very, very easy. It just wants you now to be clever in terms of the application of principles. Ladies and gentlemen, with that being said, thank you very much from me to you. Let's meet again tomorrow at exactly 1800. We will continue and finish off work, energy, and power because I am going to give you other different sets of questions, but you will still see the principles will still be the same. So it basically says the work that you do at school for 2 3 weeks, we are actually doing it here in 2 hours with now the summaries and the science that is very, very nice and clear. So it is exactly 2000 from me to you. Thank you very much. Let's meet tomorrow at 1800. Thank you very much and have a blessed evening.
Thank you, sir.
Thank you.